Hello. In this experiment, I'm going to do a calorimetry experiment. Now, calorimetry is a practical technique which is used to measure an experimental value for the enthalpy change of reaction. And to do this, we need to do a reaction with a known quantity of reactants, and we measure the temperature. And we measure the temperature at the start of the reaction, and we measure the temperature during the reaction in order to find either the highest or lowest temperature reached, depending on whether the reaction is an exothermic or an endothermic reaction. From that temperature change, we can calculate the energy change that's being transferred, or the heat energy that's being transferred into the surroundings. And then from that heat energy change, we can calculate the enthalpy change for the reaction. I'll go through the analysis of these results a little bit later on in this video. So the reaction that I'm going to do today is a displacement reaction. So it's a reaction that takes place in a solution. And the reaction I'm going to do is between zinc and copper sulfate solution. Zinc is more reactive than copper, and so we'll get a displacement reaction, a redox reaction, where the zinc will take the place of the copper and will produce zinc sulfate plus copper. I'm going to do the reaction in a polystyrene cup. This is in order to provide some insulation, so the heat energy that's being transferred into the solution will be contained within the cup, and I'll place that into a glass beaker just for stability. Normally when we do these experiments, we use a normal accurate thermometer. These thermometers read to 0.1 degrees C, and we're currently getting a reading of about 16.05 degrees C from this thermometer. But today I'm going to use a temperature probe so I can collect the data using a laptop, and I can show you the results as we get them. So the reaction is between 25 centimeters cubed of copper sulfate, which I'm just going to pour into the beaker. So there's 25 centimeters cubed of copper sulfate. And in this weighing boat, I have weighed out 1 gram of zinc powder, and we'll do some calculations, but we should find that the zinc powder there is in excess. There's more moles of the zinc, therefore the 25 centimeters cubed of 0.5 moles per decimeter cubed copper sulfate will be our limiting reagent in this reaction. Okay, so I'm going to place the temperature probe into the solution, into the copper sulfate. I'll just let that sit for a moment or two to reach the temperature of the solution, and I'm going to start recording. So I've set this up to take a measurement every minute, and so I'm going to leave this for the next so I'm going to collect a temperature reading at 0 minutes, at 1 minute, 2 minutes, and 3 minutes. At the 4th minute, I'm not going to take a reading. Instead, I'm going to add the zinc and stir, and then I'll record a temperature every minute from the 5th minute through till about 10 minutes. It's a good idea to stir the mixture, so I'm using the temperature probe to stir it, just to keep an even temperature throughout that solution. Okay, so we're just coming up to the 4th minute now. and in it goes. And I'll give that a good stir. So the temperature stabilised at about 15.9 degrees C. So as I stir it, I can see that there is a reaction going on. The copper sulfate, which was blue, is starting to become a bit paler. Okay, so that's all the data collected. And what I'm going to do next is to plot a graph of the results in order to be able to calculate the temperature change, the maximum temperature change that we would have had if all of the heat had been transferred to the water immediately. Water takes a little while to heat up, and so therefore it will be losing heat all the time that it is warming up out through the surface of the beaker, etc. I'm just going to filter off this mixture, and then I'm going to plot a graph and analyse the results of this experiment. Okay, so here are the results of the experiment. So I've written out the equation there and then copied the temperature results from that we obtained from the data logger. I've not included a temperature at 4 minutes because that's the moment where I mixed the solutions or mixed the zinc with the copper sulfate, and so if you were manually recording the temperature, you wouldn't normally take a reading at that time. And then I've recorded all the other results. So in order to analyse this experiment, the first thing that we need to do is to calculate the quantity of heat that has been released into the surroundings. And that quantity of heat is given the symbol Q and is measured in joules. And the equation to measure that quantity of heat is Q is equal to mc delta T, where m is the mass of solution, so the mass of water that got heated up. C is the specific heat capacity of water and has a value of 4.18 joules per gram per Kelvin. So that's the amount of energy you need to heat 1 gram of water by 1 degree C or 1 Kelvin. The increase is the same in both Celsius and in Kelvin. And then delta T is the change in temperature. Now, in order to measure a value for delta T, the change in temperature, what we need to do is to plot a graph of our results. Okay, so here I've got a graph of the results, which I've plotted the results onto. So we have time across the x-axis and then temperature on the y-axis. So I have recorded the temperature in Celsius because, as I say, the change in temperature would be the same in both Celsius and in Kelvin. Now you'll notice that the axes, the scale of these axes, I've chosen so that my plotted points cover more than half of the graph paper in both directions. There's certainly no need to take the temperature axis down to 0 because 0 degrees C isn't it's a made-up temperature, but it's also not a temperature that's involved in this particular reaction. So I've started the y-axis at 15 degrees C and have gone up to 39 degrees C. So you can see that we've plotted our points before we mixed the zinc with the copper sulfate, and we can see we've got a fairly stable temperature there at 15.9 degrees. Once we mixed these two, there was a rapid increase in temperature. It's an exothermic reaction, and then the temperature started to fall away once that reaction had finished. Now, whilst the water was heating up, you'll notice it doesn't heat up instantly. It takes a little time for the water to reach its maximum temperature. And all the time that the water is heating up, it will also be losing heat into the surroundings. And so, therefore, to account for that lost energy, in order to find out what the maximum value of delta T would be if the water was able to heat up immediately with no heat loss, what we can do is we can draw our lines, so we can extrapolate this line to the 4th minute. So the start temperature there would be 15.9 degrees, but we can also extrapolate this part of the graph, and we can extrapolate this line to find out what the maximum temperature would have been at 4 minutes. So I'm just going to extrapolate these lines. So my line at the start, we're fairly constant there to 15.9 degrees. And then to extrapolate this line, I look at the points that are decreasing in temperature, find a best fit line through those points, and extrapolate that line to the 4th minute. So there we have a temperature at the 4th minute, and the temperature at the 4th minute would record at 39.6 degrees Celsius. So therefore my minimum temperature down here is 15.9 degrees, and the maximum temperature will be 39.6 degrees, which gives us a change in temperature of 23.7 degrees C. Okay, so now looking at my analysis, so the quantity of heat, so the mass of solution will be 25 grams because we used 25 centimetres cubed of the copper sulfate solution. The specific heat capacity of water, 4.18 joules per gram per Kelvin, and the change in temperature is 23.7 degrees C or Kelvin. Putting those numbers together gives us an amount of heat released into the surroundings of 2,476.65 joules. So that's the amount of heat released into the surroundings. Now, the next thing we need to do is to calculate how much reaction took place. So, looking at our equation there, we had 1 gram of zinc, and we had 25 centimetres cubed of 0.5 moles per decimetre cubed copper sulfate. So I can calculate my moles of each reactant. So the zinc, the number of moles of zinc will be calculated by the mass divided by the relative atomic mass. So that's 1 divided by 65.4, which gives us a number of moles of 0.0153. And the moles of copper sulfate will be concentration times volume, so 0.5 times 0.025, and so that's 25 centimetres cubed divided by 1,000, converting the centimetres cubed to decimetres cubed, gives us 0.0125 moles. And from these you can see that they react in a one-to-one ratio. And there are fewer moles of copper than there are of zinc, and so therefore the copper sulfate will be the limiting reagent in this reaction, and so that will control the amount of reaction that occurred here. So now we can calculate the enthalpy change of reaction. So the enthalpy change of reaction we can calculate from minus Q, because the enthalpy change in the reaction is opposite to the energy change in the surroundings, because energy cannot be created or destroyed. So because delta H and Q are equal and opposite, that's why we need the minus there. But delta H is calculated in kilojoules per mole, Q is in joules. So to convert joules to kilojoules, we divide by 1,000, and to convert into kilojoules per mole, we need to divide by the number of moles of reaction. Okay, so putting the numbers in, we've got Q was 2476.65, 1,000 times number of moles of the limiting reagent 0.0125, and that gives us minus 198.1 kilojoules per mole. And that's the enthalpy change of reaction as calculated by that experiment. So the final step in this process is to carry out an error analysis. And so we've got our value for the enthalpy of reaction, and now we need to consider the errors that are caused by the uncertainties associated with the apparatus. So we've used two pieces of apparatus to give measurements, which we've used in our calculations. So the measuring cylinder, which we use to measure the volume of the copper sulfate, and the thermometer, which we use to measure the temperature. We don't need to worry about the balance because the zinc was in excess, so therefore any uncertainty associated with that won't affect the overall result. So the uncertainty in the measuring cylinder, each division on the measuring cylinder is at 1 centimetre cubed, so therefore the uncertainty would be plus or minus half of 1, so 0.5. So we've got 0.5 divided by the volume, which was 25, times 100 gives a 2% error on the measuring cylinder. The thermometer, each division on the thermometer is at 0.1 degrees, so therefore the uncertainty would be plus or minus 0.05 degrees. And because we've taken two thermometer readings, an initial and a final, our overall uncertainty will be plus or minus 0.1. Our temperature change was 23.7 degrees, so 0.1 divided by 23.7 times 100 gives us 0.4%. Add those two together gives us an overall uncertainty for the apparatus of plus or minus 2.4%. 2.4% of 198 kilojoules rounds up to 5 kilojoules, so therefore our final answer is the enthalpy change is minus 198 plus or minus 5 kilojoules per mole, and that's our answer. And then finally we can look at the experimental error. The data book value for the delta H for that reaction is minus 219 kilojoules per mole. Our answer was minus 198 kilojoules per mole. So the difference between those two values is 21. So 21 divided by the textbook value 219 times 100 gives us a 9.6% error. Now that error is obviously greater than 2.4%, so therefore the error in our final answer cannot just be explained from the uncertainties in the apparatus. It's likely that some heat has been lost that we've not accounted for by extrapolating the graph. And it's also possible that perhaps the concentration of the copper sulfate wasn't exactly 0.5 moles per decimeter cubed, and obviously we've used that in our calculation to calculate the number of moles of the reaction, so that could also have an impact on our overall result. So that experiment then shows you how to carry out a calorimetry experiment and how to analyse the results of that experiment. In a separate video, I'm going to show you how you can carry out a calorimetry experiment for a combustion reaction, which obviously can't take place in a polystyrene cup.